Hello everyone, I am Hrishikesh. This is my C assignment. Its topic is sorting by partitioning. Let us take a look at design of quicksort. It follows the divide and conquer paradigm. In divide, we separate the array into two subarrays. In conquer, we sort the two subarrays by recursive calls to quicksort. And in combine, the subarrays are sorted in place. This is the sample pseudocode. Let us take a look at an example of sorting by partitioning. Steps of partitioning. First, we select the last element in the subarray as the pivot. As the procedure executes, the array is partitioned into four regions. The above hold before each iteration of the for loop and constitute a loop invariant. Correctness of partition. In it we use loop invariant. It is of two steps: initialization before first iteration and maintenance. It is of two cases. Case 1, increment of j only, and loop invariant is maintained. This is the case 1 in maintenance. This is the case 2 of maintenance. In increment of I, swapping of a of I and a of j occurs, and in increment of j, a of r is altered. The third step of correctness of partition is termination. In it, when the loop terminates, all the elements in A are partitioned into one of the three cases. The last two lines swap. A key step in the quicksort algorithm is partitioning the array. We choose some number p in the array to use as a pivot. We partition the array into three parts. Let us take a look at alternative partitioning. First, we choose an array value to use as a pivot. Then, starting from the left hand, find the first element that is greater than or equal to the pivot. Searching backward from the right hand, find the first element that is less than the pivot. Interchange these two elements. Repeat searching from where we left off until done. This is an example for partitioning. Let us analyze the quicksort. Suppose each partition operation divides the array almost exactly in half, then the depth of recursion in log to n, because that how many times we can have n. We note that each partition is linear over its subarray. All the partitions at one level cover the array. This is the visual representation of partitioning at various levels. Going on to best and worst case analysis. This is the best case analysis. We cut the array size in half each time. So the depth of recursion in log to n at each level of the recursion. All the partitions at that level do work that is linear in n. Hence the best case quicksort has time complexity. In worst case, partitioning always divides the size n array into these three parts: a length 1 part containing the pivot itself, a length 0 part, and a length n-1 part containing everything else. We don't recur on the 0 length part. Recurring on the length n-1 part requires recurring to depth n-1. Let us take a look at the visual representation of worst case partitioning. Worst case for quicksort. In it, recursion may be n levels deep. but the partitioning work done at each level is still n. So the worst case for quicksort is O of n square. There are many arrangements that could make this happen. Here are two common cases. First is the when the array is already sorted and when the array is inversely sorted. There are some typical cases for quicksort. If the array is sorted to begin with, quicksort is terrible O of n square. It is possible to construct other bad cases. However, quicksort is usually O of n log to n. The constants are so good that quicksort is generally the faster algorithm. Most real-world sorting is done by quicksort. How do we pick a better pivot? Before we picked the first element of the subarray to use as a pivot, if the array is already sorted, this results in O of n square behavior. It's now better if we pick the last element. We could do an optimal quicksort if we always picked a pivot value that exactly cuts the array in half. Such a value is called median. Half of the values in the array are larger, half are smaller. The easier way to find the median is to sort the array in and pick the value in the middle. Median of 3. Obviously, it doesn't make sense to sort the array in order to find the median to use as a pivot. Instead, compare just 3 elements of our array, the first, the last and the middle. Take the median of these 3 as the pivot. It's possible to construct cases which will make this technique O of n square. Quicksort for small arrays. For very small arrays, n less than or equal to 20, quicksort does not perform as well as insertion sort. A good cutoff range is n equals to 10. Switching to insertion sort for small arrays can save about 15% in the running time. Let us take a look at merge sort versus quicksort. Both run in O of n log n. Merge sort is done always, quicksort is on an average. Compared with quicksort, merge sort has less number of comparisons but large number of moving elements. In Java, an element comparison is expensive but moving elements is cheap. Therefore, merge sort is used in the standard Java library for generic sorting. This is my C assignment. Thank you all.